Coming to the instrumentation of IR spectroscopy, there are three types of instruments for IR instrumented absorption available commercially. First is dispersive grating spectrophotometers that are used primarily for qualitative work. Now, when we say dispersive gratings, that grating monochromators are used in that. Okay, so their construction will be very much similar to your UV spectroscope. Okay, then there is second type, multiplex instruments employing Fourier transform that are suitable for both qualitative and quantitative infrared instruments. Now you have studied FTIR in your BFARM. So this is second type of instrument. Okay, there are no monochromators used here. Instead of that, what you have is something called as Fourier transform. Third type, we have non-dispersive photometers that have been developed for quantitative determination of a variety of organic species in the atmosphere by absorption, emission, and reflectance spectroscopy. Now, these non-dispersive, we are also going to study. What are they? You have not seen them as of now. Now, observe this instrument. Here is the IR source. From mirror, light is getting in the interferometer. From interferometer, one of the ray is getting directed through beam splitter over here. Here you have got sample. From sample, the beam goes to the detector. Now, you may observe that there is a ray of light going along the original infrared source. Does anybody remember what that light is? It is a laser of fixed wavelength. Okay, so when it is going along with the original infrared radiation, the detector will detect its interference pattern, which will be used as the scale for the interferogram. Okay, now here observe, here is block diagram over here. It is the same instrument. You have IR source. From IR source, the light is, say, getting produced. You have one fixed mirror, one interferometer, and then you have the laser transducer. Okay. There is another way of representing the same thing. IR transducer is your detector. Now here monochromator is used. All these instruments were utilizing interferometer. Now in this particular instrument, monochromator is used. The beam of infrared radiation is split into two. One is passing through sample, the other is passing through reference. Then with the half mirrors, choppers, it is forming into, it's going into the monochromator, then it is going to the transducer. Now, one difference you will observe is in case of UV, there was first monochromator, then sample was kept, but over here the beam first travels through the sample, then it enters the monochromator. Now we will see the instrumentation related aspect again, but I want you people to observe this specific type of motions within the molecule. These are the molecules over here, and these are the specific motions. Even just go through them. Here the plus and minus do not indicate charge, they indicate the motion. Go through the chart. I will give you some time. Let us continue our discussion now related to the sample preparation and the instrument of IR spectroscopy. The IR spectroscopy is applied to the qualitative and quantitative determination of molecular species of all type. The most widely used region in the infrared region is mid-infrared. We have seen this. We have seen this range. In this range, everything like absorption, reflection, emission spectra can be obtained from the compound. The infrared region from 4000 centimeter inverse to 14,000 centimeter inverse, that is 0.75 to 2.5 micrometer, also finds considerable use for the routine quantitative determination. Now this is very water, CO2, low concentration hydrocarbons, amine, nitrogen, and many other compounds can be detected quantitatively in this region. The far infrared region has been for the determination of the structures of inorganic and metal organic species. For organic species alone, the region, far infrared region, is not that useful. Now, the reason being the bond between those inorganic compounds are strongly ionic bonds. So characteristic of the vibration for those ionic bonds is different than the the mid IR region. So this table in front of you states the application of different spectral regions, what measurement type can be utilized, and which are the applicable samples through it. Like for near IR region, the measurement, the type of instrument that is used is diffuse reflectance and also absorption. You have studied diffuse reflectance in your BPharm, but near IR is majority quantitative. Qualitative measurements are rarely possible. What it can measure, it can identify gaseous mixtures, mid IR absorption, reflectance, and emission. All three are possible. In case of absorption, it can be qualitative, quantitative, or it can be combined with chromatography like LC or GC or HPLC. So it can be used in combination. So the corresponding application is it can qualitatively measure pure solids, liquids, or gases. It can quantify complex liquids. When we say complex liquid, it means there is mixture of different liquids in it, mixture of solids or gaseous mixtures. If it is combined with chromatography, again liquid, solid, and gaseous mixtures can be studied. In case of reflectance, qualitative, pure solids or liquids. Emission, it is mostly quantitative. Atmospheric samples can be studied. In case of far IR, only absorption spectroscopy is possible, which is qualitative and can analyze pure inorganic and organometallic species. Now, coming to the sample handling in mid-infrared region. Now, when you consider IR and its sample handling, the challenging part is in what solution you will dissolve your sample, because almost all the solvents, they absorb IR right by themselves. Because if you consider even simplest of hydrocarbons which can be used as solvent, there is carbon hydrogen bond in it, and carbon hydrogen bond is polar because electronegativity difference exists between carbon and hydrogen. So let's start sample handling. No good solvent exists that are transparent throughout the IR region. As a consequence, sample handling is frequently the most difficult and time consuming part of IR spectrometric analysis. In case of gaseous samples, the spectrum of a low boiling liquid gas can be obtained by permitting the sample to be expanded into an evacuated cylindrical cell equipped with suitable window. Now the problem with gaseous sample, another problem is you require significant number of molecules that will give you absorption and you will get significant height of the peak. So gases, because they are rare in nature, will require a lot of gas or a lot of boiling liquid producing that gas. So the chamber through which the IR goes travels, IR radiation travels is large chambers, or at least you will require several reflection of the IR radiation while it is passing through it. A gas sample cell contains a cylindrical glass or sometimes metal. So this is the glass tube which you can observe over here. There is opening at here, there will be opening at here also, at this end also. The cell is closed at both ends with an appropriate window material, generally which is NaCl or KBr. Both the materials are transparent over IR region and equipped with valves. You can see these valves over here, or stopcocks for introduction of the sample. The sample is gas, please remember that. Long path length, more than 10 centimeter cells used to study dilute. When we say dilute, it is expected to have fewer molecules or weakly absorbing samples. Multiple cells, uh, multi-pass cells. These multi-pass cells are more compact and efficient instead of long path cells. Now what happens is, instead of using this long path cell, you will use arrangement like, suppose there is, try to show by diagram, suppose from here the light is entering, IR light is entering, you will have multiple reflectors from which the light is bouncing multiple times. If light has to pass in a single, along the single path, it will travel the less distance, but in this zigzag manner it will travel more distance, so there will be more significant absorbance associated with it. Okay, to resolve the rotation structure of the sample, the cell must be capable of being evacuated to measure spectrum at reduced pressure. When you reduce the pressure, the molecule, instead of vibrating more, they will express more rotational and translational motions. So that can be utilized by reducing the pressure in the cell. For quantitative determination with light molecules, the cell is sometimes pressurized in order to broaden the rotation structure and all sample measurement. Okay, that was related to gases. Now coming to the solution, a convenient way of obtaining infrared spectra is on solution prepared to contain a known concentration of the sample. It is same as preparing a standard solution. This technique is somewhat limited in its application, however, by availability of solvents that are transparent over significant region in the infrared. Now, which solvents can be used? Obviously, it should be transparent. No single solvent is transparent throughout the entire mid-infrared region. Water and alcohols are seldom employed, they cannot be employed. The main reason is KBr or KCl, they dissolve in water and alcohol, so they cannot be employed. Not only because they absorb strongly, but also because they attack alkali metal halides, the most common materials used for cell windows. These are different solvents, and the blue line against the name of the solvent indicate the range in which they absorb the IR light. Okay, so for the solutions, which cells are employed? So Sodium chloride windows are most commonly employed for these cells. Okay. Even with care, however, their surfaces eventually become fog due to absorption of moisture. Over a period of time, sodium chloride absorbs moisture, so the surface of this window becomes foggy. Polishing with buffing powder returns them to their original condition. So they have to polish frequently to maintain their optical characteristic. Now, liquids. Now, till now we were looking at solutions. Now, liquids. When the amount of liquid sample is small or when the suitable solvent is unavailable, it is common practice to obtain spectra on pure or neat liquid. A drop of neat liquid is squeezed between two rock plates to give layer that has thickness 0.01 millimeter or even less. Now, when the two plates hold together, then mounted in the beam path, such technique does not give reproducible transmittance data because it is very difficult to get a uniform layer throughout. But the resulting spectra usually is satisfactory and qualitative investigations can be done. So those beads, those plates made up of say KBR or KCl, they are over here. In between them, you will have the liquid. You can see there is a gasket here. One plate will be kept there. Then you will add few drops of liquid on that. The other plate will be kept between these screw, and using these nuts, it will be you can say tightened over there. And after tightening, you can mount them over here in IR spectra. It will look something like this. This is another representation of the same thing. These are the two metal halide windows. There is a spacer or gasket over here. Here will sit the liquid. It will be sandwiched between two windows. Then these neoprene gaskets will hold these windows together on these screws. Okay. There is another way. There may be a small sample cell. The windows are made up of KBR. In this sample cell, few ml of the sample is loaded. You can see there is space to attach these two hinges of the sample cell, and then it is mounted over here in the path length of infrared light. Example of IR spectra, carbon tetrachloride. There is no peak for CH. Both these peaks are because of CCl stretching. One for symmetric, the other for asymmetric. Now, these are common window materials. See, first three are very common. Sodium chloride, potassium bromide, potassium chloride. Go through the list. Okay, we have now seen gases, we have seen solutions, we have seen liquids. Now coming to the solids. Now, most organic compounds exhibit numerous absorption peaks throughout the mid-infrared region. And finding solvent that does not have overlapping peaks is often impossible. There will be always overlapping peaks. As a consequence, spectra are often obtained on a dispersion of a solid in liquid or solid matrix. So, because of the dispersion, you will get more confined peak. Okay, there are many ways of preparing samples, solid samples. First is pallating. Well, this is one of the most popular techniques of handling solid sample, and it involves pallating with KBR. A milligram or even less of the sample which is finely ground is taken and it is mixed with approximately 100 milligram of absolutely dried potassium bromide powder. Now, potassium bromide has tendency to absorb moisture, so it should be dried always. It is generally kept in desiccator. The mixture is then pressed in a die at 10,000 to 15,000 pounds per square inches, that is psi, to yield a transparent disc. The pressure is so high that KBr becomes transparent. The disc is then held in the instrument beam for spectroscopic determination. This is the hydraulic press. Now, here it is the, you can say, lower platform. On the lower platform, in a cavity, KBr along with sample is kept, and the cavity is closed over, and then there is a piston, there is a hydraulic pump over here. See, hydraulic handle is there. You press it from the bottom, it gets pressed upwards. These are big support. So when it is lowered, you get a compressed pallet in KBr. Thing that is kept over here, the cavity which I told you, is it does that look something like this. There is another manual method of preparing the pallet. In this cavity, you fill KBr. यहाँ पे उसका powder बनाया, mixed with the sample placed in it. Okay, the screw is tight over here, made tight over here. इससे वो घुमाया जाता है and it is made tight, and you will get pallet at the end. Now, there is another technique called as Mull technique. Mull is another name for suspensions. Okay, what they do in that, infrared spectra of solid are not spectra of solids that are not soluble in an IR transparent solvent or are not conveniently palleted in KBr are often obtained by dispersing the analyte in mineral oil or fluorinated hydrocarbon mulls. So basically, some type of oil or fluorinated hydrocarbons are added to the sample. Then mulls or suspensions are formed by grinding 2 to 5 milligram of finely powdered sample in the presence of 1 or 2 drops of heavy hydrocarbon oil called as nuzol. If hydrocarbon bands interfere, fluorolube, a hydrogenated polymer, can be used. This will not interfere. The resulting mull is then examined as a film between flat salt plates, same as you observe the solutions. Now, the sample handling is over. Now coming to the reflectance techniques in infrared. It is called as infrared reflection spectroscopy. Now, infrared reflection spectroscopy has found a number of applications, particularly in dealing with solid samples that are difficult to handle, such as polymer films, fibers, food, rubbers, agriculture products, and many other, including food items. Now, mid-IR reflection spectra are similar in general to appearance as normal spectra and provide the same information as the absorption spectra. The reflectance spectra can be used in both qualitative and quantitative analysis. Now, usually there are adapters. Okay, these adapters are provided to fit in a cell compartment to change the IR instrument from absorption to reflection. So you don't have to change the entire instrument. In your instrument, you need to just fit those adapters, and you will use the same instrument for reflectance than absorption. Now, the phenomena between transmission and reflection, I think I can skip this part. This much you can understand. Now, the surface there are certain other types of reflections. See, this is difference between reflection and transmission. In reflection also there are certain types of reflections. There is internal reflection spectroscopy where the IR enters, this is your substance, analyte, it enters within the substance and then get reflected. It is related to attenuated total reflection because the reflection is attenuated because it is entering in the substance. Less quantity is getting reflected. Then there is external reflection spectroscopy, meaning from the surface itself, the IR light is getting reflected. It is called as specular reflection. Then there is combination of internal and external reflection. There is combination of these two. It is called as diffuse reflection. Short form is drifts through the surface. So IR light entering the surface, some part is bouncing off, some part entering and getting dispersed in all the direction. Go through these three diagrams. In case of reflection, there is some basis of the sampling techniques. Now, this involves measurement of the reflected energy from the sample surface at a given angle of incidence. Now please remember that molecules that are exhibiting this phenomena, they will be relatively smaller in number as compared to transmittance. In transmittance, IR light is passing through the sample. In reflectance, it is the surface phenomena. So the number of molecules involved will be less in number. Okay. The electromagnetic reflectance depends on first the angle of incidence of the illumination beam, second the refractive index and the thickness of the sample, third experimental conditions. Now, types of specular reflection experiments. When we say specular, we are actually referring to this type. Now, reflection absorption relatively of thin films on reflective substances measured at nearly normal angles of the incidence. Specular reflectance measurements of relatively thick samples measured at near normal angle of the incident. Then angle reflection absorption of ultra thin films or monolayers deposited on the surfaces measured at high angle of incidences. Let's come to the first part. Attenuated total reflectance is also abbreviated as ATR. Now, the green part is your sample. There is incident beam. If at the point of its contact with the sample, if you know the perpendicular, the angle it is making is theta, and this is the reflected beam. Now, in contact with sample, you need to keep internal reflection element. This have a low optical density in IR region as compared to sample. What happens is the incident beam arrives, hits the sample, and some part of it enters the sample. So the reflected beam has some missing wavelengths. Those missing wavelengths will be absorbed by the sample itself. So this is the working principle of ATR, attenuated total reflectance. There may be if the absorption by single reflectance, as it is getting reflected only once from the sample. So it may happen that the absorption is very weak. So in that case, what is done is there is one reflective surface kept on the uh, element. Okay, and then you have sample over here. So when the light enters the element, it bounces several times before getting off, and from here it is measured. Okay, what are the factors influencing ATR analysis? Wavelength, refractive index of sample and the element, angle of incidence of IR radiation, depth of penetration, the sample and element contact efficiency. Now, this particular diagram shows the difference of the angle of incident IR radiation. Here it is 30 degrees, here it is 45 degrees, and here it is 60 degrees. As you will see that as the angle is increasing, the intensity of the peak is getting decreased. There is another can say another expression, another way of representing the ATR cell. So in summary, if you talk about ATR, it is very versatile, non-destructive technique for variety of materials. It requires very less or almost no sample preparation. It is used for surface characterization, opaque samples. It has limitation also. Sensitivity is typically 3 to 4 orders of magnitude less than transmission because number of molecules interacting with IR is less. Now coming ATR ho gaya. Now second is specular reflectance. It is used for smooth surfaces. Now for smooth surfaces, angle of reflectance is equal to angle of reflection. That means reflection and reflectance is occurring simultaneously along the same lines. For examining smooth surfaces only of solid or coated solid, this particular thing is useful. Now, specular reflectance sampling in FTIR represents a very important technique used for measurement of thin films on a reflective surface, analysis of bulk materials, measurement of monomolecular layers on substance material. Now, often sample analysis with no sample preparation is required, so this is not as popular as other reflection techniques because it has got limited applications. Third type is diffuse reflectance spectroscopy. Now, when we say diffuse, it means you cannot predict the way in which the reflection will occur. The surface is uneven. So, for this, drifts are used diffuse reflectance IR Fourier transform spectroscopy, and it has one additional, you can say, material, ellipsoid mirror. The surface of the mirror is elliptical, half the elliptical, I should say. So when from interferometer light comes here, it will go in the sample and it will get directed in all the directions, reflected in all the directions. But because of this ellipsoid mirror, it will get focused to the detector. Applications of drifts. Now, it is useful for very strongly absorbing samples like coal, pharmaceutical, plastics, small irregular samples, and also powders. What is the advantage? Minimal sample penetration and sample is not destroyed. Again, comparison. Now, coming to the qualitative analysis. Now we are looking at now applications. It is the IR technique is used for quantifying organic, inorganic, and biological species. The time required to perform this ATR analysis, structural determination was reduced by factor of 10, 100, or even 1000 by FTIR modern instrument because you don't have to take the monochromator, change the wavelength. Here you can bombard all the wavelengths simultaneously. Identification of an organic compound is a two-step process. In first step, it involves determination of what functional groups are present, most likely to be present by examining the group frequency region. In second step, the detailed comparison of the spectrum of unknown with the spectra of pure compounds that contain all the functional group in the first step. So second step is detailed analysis. The fingerprint region, which extends from 1200 to 600 centimeters, is particularly useful because small differences in the structure and constitution of the molecule results in significant change in the appearance of the distribution and absorption spectra in this region. Observe the IR spectra over here of N-hexane. In N-hexane, you must be expecting all the CH bonds to vibrate, so there will be stretching and bending vibration. These two peaks are because of bending, and these diffused peaks are because of stretching. These are the corresponding frequencies. Now let's look into the group frequency. Every group, functional group, has typical frequencies associated with it. Go through the table, different functional groups, types of compounds, and the frequency associated with, along with the intensity of the peak. We'll give you 2 minutes, go through this table. Okay, let's proceed. The spectra will always, you can divide into two halves. On the right hand side you have fingerprint region, and on the left hand side you have group frequencies. Different functional groups and corresponding frequencies. With this, we have done with IR spectroscopy. These PPTs I am going to upload on your Google Classroom. These are various examples, you can study them. Okay, near IR spectra, these are advantages and disadvantages. It is very much similar in the concept with normal IR spectroscopy.